Continuing with factoring, here is the notes for 6.4. So remembering in all of this, we keep talking about the fact that the type of factoring you do is dependent on how many terms you're talking about. If there's 3 terms, you're going to want to backwards FOIL, either by using the guess and check method or using the grouping method that I've shown you in the last 2 sections. If there's 4 terms or more than 3 terms, you're going to do grouping. And again, 98% of the time, in fact, anything really you guys are going to see, it's going to be grouping them 2 and 2. You'll be doing other things in your next math class. And then always taking a greatest common factor out first before you do any of those things. So now we're into factoring binomials. And this is the last one. So good. That's a good thing. So if you have a binomial, which means 2 terms, there are actually 3 different possibilities for factoring. Okay. So if we look at this, one of the types of factoring is the difference of 2 squares. So remembering difference means subtraction. So it's the difference of 2 perfect squares. If you are looking at the difference of 2 perfect squares, it will always factor into the square root of the first one plus the square root of the second one and the square root minus the square root. And again, that works because remember back when we were doing FOILing, if you had 2 binomials that were exactly the same except for the sign, do you remember that I said you really didn't have to do the whole FOIL? You just had to FLA because the O and the I will always drop out. And you can see that if I multiply these 2 binomials together, I would have a squared. Outside, I'd have negative AB. Inside, I'd have positive AB. Those are going to cancel out. And then you're just going to have a negative B squared at the end. So once you identify it as a difference of 2 squares, it's totally easy to factor. Look. A squared minus 16. It is a difference of 2 perfect squares. It's going to factor into a plus 4 times a minus 4. And bam, you're done. Now again, you can always FOIL them or FLA them back together to make sure, as a check. Is this a difference of 2 perfect squares? Absolutely. And it factors into 5x plus 1 times 5x minus 1. See how it works? How about this one? Is it a difference of 2 squares? Absolutely it is. So it would be 4x plus 7y, that's the square roots of each one of them, times 4x minus 7y. It's always the square root plus the square root times the square root minus the square root. How about this one? Are these 2 both perfect squares? Absolutely. It's going to be z minus 3/4 because that is the square root of 9/16 times z plus 3/4. How about this one? Is it a difference of 2 squares? Sure is. What's the square root of m to the 4th? It'd be m squared plus, what is the square root of n to the 14th? That would be n to the 7th. Take half of the exponent times m squared minus n to the 7th. Let's look at this one. Can I take the square root of both of these? Yes, this is actually a perfect square. This is 16 squared if you don't happen to know that. So it's going to be p squared plus 16 times p squared minus 16. Now, here's something that's a little tricky. You are not done. You are never done with factoring, and this really hasn't come up too much except for taking out a greatest common factor, but you're never really done with factoring until everything at the end can't be factored any further. I think that's very logical. This cannot be factored any further. It is prime. But look at this. Do you see where this is also a difference of 2 squares? So look, the first one stays because it's a sum. It doesn't factor any further, but this guy can factor into p plus 4 times p minus 4. And now you are done. How tricky is that? Speaking of tricky, can I factor this? I cannot, because it is not a difference of two squares. It's a sum. So we would write prime for this one. Let's look at h. Well, hopefully you notice that I can take out a GCF of x before I do anything else, which leaves me 9x squared minus 25. Now we look here. Is this a difference of two squares? It sure is. So it factors into 3x plus 5 times 3x minus 5. How about this one right here? Well, it certainly isn't a difference of squares right now, but do you notice that there's a greatest common factor of 3? In fact, I'm going to take out a negative 3 because I told you I hate that negative there. So if I take out a negative 3, I'm going to get positive 16x to the 4th, and 3 divided by negative 3 is negative 1. Is this a greatest common, or not a greatest common factor, a difference of two squares? It is. So it will factor into 4x squared, because that's the square root of here, plus 1 times 4x squared minus 1. Am I done? This does not factor any further, but how about this? This is again a difference of two squares. So this is going to break down even further. So let's see, we're going to have negative 3. 4x squared plus 1 does not, because it's a plus. This will break down into 2x, because that's the square root of 4x squared plus 1 times 2x minus 1. And now finally, I'm done. All right, let me just stack my papers here if you don't mind. So that's squares. What about cubes? You can actually factor the sum of two cubes, and you can factor the difference of two cubes. Unlike squares, you can only factor the difference of squares. But you can factor both of them. And here are the rules. Now, I am sorry, but the only way you are going to be able to do this is to memorize these rules. There's no trick I can, well, there's a little trick, but there's really no big trick that I can tell you. You have to memorize the rules. Okay, so if you look at the difference between the two factored forms, does everybody see that really the only difference is the order of these two symbols, right? This is plus minus, and this is minus plus. The last one's always plus. That's the only difference. So when you factor a sum or a difference of cubes, you will always have a binomial times a trinomial. The binomial, the sign will be the same as the original problem. Then it's the opposite sign of whatever that is, and this is always positive. So same as the original problem, the opposite of that, always positive. What does that spell? SOAP. That is a way to be able to remember what your signs are. Same as the problem, opposite of that, and always positive. All right, so memorize that. So here we go. We have 6 of these to go ahead and factor. If you know the rule, then it's easy. So here's what you want to do. Here's how kind of I have memorized it. We're going to factor these. So this is going to be a sum of cubes. Now, what is the cube root of x cubed? It's an x, and I always put that really small right below that. And what is the cube root of 27? It's 3. These are your A and your B from these rules up here. Your A is x and your B is 3. So we know it's going to be a binomial times a trinomial. So once you've identified your A and your B, it's just plugging it into the formula. So in my binomial, it's going to be x plus 3, same sign as here, so it's this plus this. In the trinomial, you square the first one, opposite sign, multiply these two things together. That's the AB, so that's 3x, always positive, and then you square the last one, and 3 squared is 9, and you are done. And the good news is you never have to check to see if this was prime, because I am promising you, if you have factored by either doing a difference or a sum of cubes, the trinomial will never factor any further. All right, let's do B. This is going to be a difference of 2 cubes. So the cube root of c cubed is c, and the cube root of 8 is 2. So it's a binomial times a trinomial. This binomial will be c minus 2, because it's the same sign as the problem. Then you square the first thing, that's c squared, opposite sign, multiply them together, that's 2c, always positive, and square the last number, that's going to be 4. Done. C, it's going to be a sum of 2 cubes. What's the cube root of 125y cubed? It is 5y. What's the cube root of 1? It's 1. Here we go. Binomial, trinomial. 5y plus 1 in the binomial, the same sign. Square the first one. That's going to be 25y squared. That's what I get when I square this. Opposite sign, multiply them together. That's 5y, always positive, square the last one, and 1 squared is 1. And you are done. Now look at D. You say, well, these are not perfect squares. But maybe there's a GCF, and there is. I can take a 2 out of both of these terms, which is going to give me 27x cubed minus 64y cubed. And guess what? Now it is a difference of cubes. The cube root of 27x cubed is 3x, and the cube root of 64y cubed is 4y. So here we go. Let's not forget the 2. We're going to have a binomial times a trinomial. So now inside the binomial will be 3x minus 4y. First in the trinomial, you square the first little guy, so that's going to be 9x squared, opposite sign. Multiply the 2 little guys together, that's 12xy, always positive. And then you square the last little guy, that's 4y, so it's going to be 16y squared. And you are done. Why don't you go ahead and do E and F on your own, and then come back and watch me do them. So for E, I'm going to take out a 2. There's a GCF, which will leave me with x cubed minus 27, which is a difference of cubes. And the cube root of x cubed is x. And the cube root of 27 is 3. So I'm not going to forget my 2. And I'm going to have a binomial times a trinomial. In the binomial, it's going to be x minus 3, same as sign as the problem, and then x squared. Opposite sign, multiply the 3 and the x together, always positive, and then you square the 3 to get 9. And finally, as it stands, it's not a sum of cubes, but is there a GCF? Yes, there is. I can factor out a 3. Which will leave me with 8x cubed plus 27y cubed. And now I have a sum of 2 cubes. So it's going to be 3 times a binomial and a trinomial. So the cube root of 8x cubed is 2x, and the cube root of 27y cubed is 3y. So it's 2x plus 3y. Now square the first one, that's 4x squared minus, multiply the two guys together, that's 6xy, always positive, and then you square the 3y to get 9y squared. And there's the end of 6, 4.